Welcome to today's presentation, using EDS files to program AMCI EtherNet IP motion products. For those of you who aren't familiar, you may be asking, what is an EDS file? An electronic data sheet, or EDS file, is a simple text file used by network configuration tools to help you identify network products and easily commission them on a network. Prior to the existence of EDS files, we would have to add AMCI Ethernet motion products using a generic setup. It's not a difficult process, it's a rather simple process, but what it doesn't do is provide for some of the features that the EDS file can provide, such as product-specific data types, product-defined input and output tags, and product compatibility verification. So why would I want to use an EDS file? Well, the EDS file provides for easier integration versus the Ethernet IP generic setup, which is our standard setup today. This is because the EDS file will provide for clearly defined I/O tags, and it will also implement our configuration data tags, which do not exist in an Ethernet IP generic setup. All of these features will provide for simple programming, as you will see in the presentation that follows. When we're talking about EDS files, the EDS files we can provide for our SD 17060E stepper drive, the SD 17060E2, as well as our SMD23E and SMD23E2 products. But for today's presentation, we'll only be talking about the SMD23E2. The highlights of the topics we'll be discussing will be adding an AMCI network device as a generic device. Now, we'll be doing this to kind of give you some ideas of what we're talking about, of some of the benefits of the EDS file. We'll go over installing an EDS file for those who aren't familiar with how to do that. And then we'll jump right into adding the AMCI network device using that EDS file that we just installed. And then we'll look at changing the device configuration using the configuration tags that we created. And then we'll look at the tag structure of both the input and output data registers. After doing that, we will look at creating a simple motion command using the EDS file tag structure. Let us begin our presentation. For the purposes of today's topic focus, we will assume the programmer already understands the steps required to create a new program and has a basic level of PLC programming knowledge, specifically Studio 5000 from Rockwell Automation. So getting started. Before we get started into looking exactly how EDS files are used and some of the benefits, let's take a look at how today one would add an AMCI Ethernet IP motion device to Studio 5000. The first step would be to add the device as a generic device. As we can see, once we add the device to the network, what we need to do is then select the module type. And the module type that we're going to select is going to be an Ethernet generic. Again, we're doing this as a prior to having an EDS file, so really the only way to add any device which doesn't have an EDS or is not already part of the Studio 5000 software is to add it as a generic device. So let's add it as a generic. And to do so, we have several steps we need to take. This is a step that some people miss. They do it in a hurry, fail to read the manual, and fail to set the communication format correctly. So that's something we need to be aware of. And then we set the IP address of the device. In this case, we're just going to use the network selected. Assembly instances, these can be found in the manual. Again, not everybody opens up the manual when they start this, so it can be a little bit of an issue. But all this information can be found in the user manual. So once we've done that, we've now added the device to the PLC network. We can change here the RPI if we chose to, but just for discussion's sake, we're going to leave it at the 10 milliseconds. And as you can see, that once we've created this file, and added this device to the network. We've created tags associated with that device, but those tags really are just named as generic names, data words 0 through 9 for both the input and output registers. Those names really don't have any association with any functions within the device. So it can be a little bit of a problem when doing programming for the first time. There's a lot of bit manipulation that needs to take place when doing programming, such as monitoring whether the axis is in motion, associating a bit with a move type when we're sending data to the device. So not that it's difficult, but it can be a challenge the first time you use the device. How do we overcome that? Well, oftentimes we use user-defined data types. AMCI has created some sample code along with add-on instructions, which can make programming easier, but without having the specific names for the functions of each device, it's a little bit less intuitive than it could be. And the other thing that I would like to point out here is that with the generic type, the configuration files which exist here are not used with the SMD or SMD-E2 or really any of the AMCI motion products. Those configuration files are left blank and have no association with the product. So that's something that's going to change when we take a look at the EDS files. Okay, the first step when using EDS files in Studio 5000 for AMCI motion products is to add the EDS file. To do so, you can get a copy of the EDS file from our website, www.amci.com, or contact support and they can email you a copy. Assuming you've already got a copy of it, the first step would be to add that EDS file. To do that, we go to the Tools menu, pull down, click on EDS Hardware Installation Tool. And when we do that, there will be a wizard that appears. That wizard, we're going to follow several steps to do that. We're going to click Next. We make sure that we have register and EDS file selected. And then we want to tell the wizard which file we're going to be adding. And to do so, obviously you've either downloaded it or had it emailed to you, and it's located somewhere on your PC. And that's where you want to find that file, in this case by clicking Browse. I have it on my desktop. That's already here for me. So I've located that file. In case we're doing the EDS for the SMD23E2. I'm going to click that. When that's done, we click Next, and then it lets us know that, hey, we verified that EDS file is okay. We know that's a good EDS file because we have a green check mark here. If the EDS file was found to be corrupt in some manner, we would have a little triangle with an exclamation point. But we don't. We got the green check, so we're good to go. Click Next. When we downloaded that EDS file, along with the EDS file, you saw something called a .ico file. That's an icon file, and that icon file gets associated with the EDS when you install it to Studio 5000. So when you get to this particular step within the wizard, you should see a little image that looks like this, SMD23E2. It should be or should have been located in the same folder where you located the EDS file. If that's the image that appears, or you can select the appropriate image you want, click Next. Verify the file you want to add. We're going to be doing the SMD23E2, obviously. Click Next, and we're done. Okay, with that done, the next step is going to be to add the device to our PLC network. To do that, we go over to the network area of the PLC. We're going to highlight that by clicking with our button for New Module. When the New Module pane appears, we click that. And then we come over here and try to locate that EDS. We have a lot of products we can select here. To make that simple, to locate the AMCI products, we deselect the module type vendor filters and then select only those devices which are registered as advanced microcontrols or AMCI devices. You can see we've added several devices, but the one we're talking about particularly here is the SMD23E2, so the device we want to add to our PLC program is that. Click Create. And when we do that, we're going to see this new module pane show up. And here's where we name the device. We're going to name it Motor 1, and then give it the IP address. I know the IP address of this device is 192.168.0.50. And of course, you could give it whatever IP address you need for your network, and the IP address of the device can be changed using either the AMCI Net Configurator tool or some boot P server, but with the assumption that we're going with what the default is here for demo purposes, that's the IP address we entered. Okay, once that's done, we've actually added the device to our PLC network, as you see down here. We're done adding devices, so we're going to click Close. If we wanted to add more, we would just simply select another device and click Create, but in this case, we're done. Clicking on Close. Now what we can do is take a look at what we've done with the properties of this device. If you remember when we had the generic type device, we had to select the COM format, we had to do assembly instances, set up the number of input words, output words, and our configuration words were unused. When we use the EDS, we see a much more streamlined pane. The only thing we need to worry about here is the IP address. And when we actually click on the configuration window pane, we see that we actually have configuration registers being used here. This is where we can actually set up things like the input type, what we're using them for, whether they're homing inputs, registration inputs, what have you. We set the starting speed, the motor resolution, encoder resolution, and motor current. The particular device we have here for demo purposes is not going to be using encoder, so I'm going to set that value to 0. And the motor resolution I'm going to set to 1000. And that's all done here through this pane, and I click Apply. And my device is now configured. Those values you saw there are the default values and can be changed to whatever value you need for your setup, and that's how you would do so through this configuration pane. When that's done, we click OK. Now, if I want to look at what those tags look like, once I've added that device, I click on the monitor tags, and we see they look quite different than what they did as a generic device. When I look at my input registers, I see each bit named for its function. It's telling me exactly what status information is being sent back from the device. I can see the moving bits, whether I'm moving clockwise, counterclockwise. If I'm accelerating or decelerating is also being reported. If I have any errors, those would be reported here with easy to find bits. Why this is important is when I use my logic and want to write my logic, oftentimes I want to make sure certain things are occurring or not occurring when I send a move. I want to make sure that my axis is not moving when I send a command, because if I try to send a move command while it's already moving, I'll get a command error. So I can use those bits to condition rungs of logic, and using easy to define data tags makes programming a heck of a lot easier. I also see here that I have something called a heartbeat bit. This bit is actually a bit which tells us that the device is communicating with the PLC. It actually turns on and off once per second, and is an easy way to monitor communication with the PLC and the device. And we also see that we can see our motor position and encoder position being reported in easy to find data tags. Unlike with the initial setup, which were words, 0, 1, 2, 3, 4, so on and so forth. We can certainly use those in our logic, but having nice names for them makes life a lot easier. And when I look at my output registers, I see that I have well-defined functions in my command data block. If I want to do an absolute move, I set this particular bit. If I want to do a jog and a clockwise, I set this bit. And when I'm sending it what velocity data, what position data, accel and decel, all of those words are labeled nicely for me as well. Again, generic type, they're there. Words 0 through 9, not as well defined. Another thing you'll notice here with the EDS files is we have EDS defined data types. And we see them named here, SMD23E2, config registers, E2, input registers, output registers. This is going to be important when we actually start doing programming, because we can actually use these user-defined or EDS-defined data types when we're doing our logic to set up tags that will associate with motion commands. It makes it a heck of a lot easier. I don't have to create user-defined data types. It's already done for me. Lastly, I think it's important to see here, when we created those config registers, that config data that we did in the properties pane can also be modified here in our configuration registers, which means if somewhere in our logic I want to make some changes to, say, the motor resolution, I can make those changes here. If I want to change my motor current, I have a way to do that using these configuration registers. Typically, once you have your configuration set up, you're not going to make those changes, but they are available to you if necessary. Okay, after seeing that, how do I use these data tags in my logic? How is this better for me? Well, oftentimes people want to use add-on instructions because with the generic method, it's not easy to figure out what word is what. So having a nice add-on instruction simplifies that method because it all happens behind the scenes. And AMCI has those. And we'll also have those for devices that use the EDS files, but it's pretty easy to do a motion command or really any command when we associate these EDS files, and I'm going to show you how those are done right now. When we send a motion command or any command to that matter to an AMCI Ethernet IP motion device, what we're trying to do is take a block of data which contains that command recipe, for lack of a better description, which contains that command type, whether it's a move like an absolute move or a jog move, or a clear errors command, or reset position, so on and so forth. And then those other words that we saw in that data block, which contain the velocity data, position data, anything associated with that command would all go down at the same time in that data block. And we typically do that using a copy instruction or a synchronous copy instruction of a particular length. So we're going to add one here to our logic. Okay, so we're going to do a synchronous copy. And the first thing I want to do here is create a data tag which is going to contain my command. In this case, we're going to do a move command. So I'm going to create a new tag, and we're going to call it first move. Not very original, but you get the point. And what we're going to do here for our data type is we're actually going to select the data type associated with the product that we're using, which is the SMD23E2. So we're going to use the output register data type because we're sending it to the SMD23E2 output registers. Once that's selected, we now can click Create, and we've created our first tag for sending a move down to our SMD unit. Then we just have to define where we're sending it to. And to do so, we just select the motor output registers. We're going to send it to motor 1, the output registers, obviously, because that's how we send a move to the device. The length of block of data we're sending to it is 10 words, so we enter in 10, and that's really all it takes to send a move over to the device. It's very easy. And then when we go here to our logic, to our tags, we then go to the main program tags that we created here, first move, and we define the move we're going to send to it. So in this case, I want to do a relative move, which is basically just an index move. Do a relative move, so we set that bit, scroll down through our tags here, and then we enable the driver here. If we don't enable it, it's not going to move. So we have to make sure we enable the driver. And then we tell it how far we want to go. In this case, we want to go 10,000 steps. And we want to go 1,000 steps per second. And we'll set our acceleration rates and deceleration rates. And we're done. That's all we need to do with that particular tag. And now we go back to our logic here. And I think for Demonstration purposes, what we'll do is we'll complete a couple of rungs of logic here to show you how easy it is to execute a move, and then also be able to go online with a device and see exactly how the information appears in the input register. So let's finish off that logic. What we're going to do here is just add a simple bit here to start our move. We'll call this move bit. And then what we want to do too is just to kind of show you exactly what you want to do is, like I said, you don't want to try and send a move while it's the motor is moving, because you get a command error. And you also need to understand that when you're doing a move, the move occurs on the transition of that particular command bit on a transition from 0 to 1. So if you're doing a series of relative moves, whether they're the same distance or different distances, it still needs to see a transition of 0 to 1 on that relative move bit. So what we like to do here is simply have a rung of logic where we monitor the move bits of the motor, and when we see motion, just write a 0 to the very first command word. That way we've cleared out all of those command bits, so the device is ready to receive the next command when it's necessary. So we'll monitor those bits here, and in this case, like I said, you'll see here how easy it is to look at those tags and implement them in our logic here. So we want to check to see we've got our move clockwise bit, and then we also want to make sure, okay, is it moving counterclockwise? When it's moving in either direction, we want to clear that command word. So that's how we do that. And then in this case, since we only want to really clear out the command word, we really only need to move one word over to the device to clear out the very first word. So we're just going to do a move here of 0, which is going to send a value of 0 over to that register and clear out any bits in that command word. And that command word, again, is going to be motor word output word 0, and we are good to go. How did that happen? Okay, that's done. Now that that's completed, we can actually download this to our PLC, and we're ready to rock and roll. Okay, I didn't make you witness the downloading and going online of the PLC program. You all know how that's done, so no sense showing that. But what I want to show you is exactly what the input registers are seeing when we're communicating with a device and doing a run command. So if I look here at my input registers, you see here the information coming back from the device. Right now it's telling us that our axis is stopped, so it's at rest. We see that the module OK bit is on, so our hardware is working correctly. We have the heartbeat bit going on and off as expected, and it's actually also telling us what the current is set to in the motor. If that value was set to a different value, we would see that here. And we see our motor position here is a 0, and we'll show you what happens to that position value after we do a couple of moves. So in our logic, again, 2 lines of code is really all it takes to initiate a move with one of these devices. If I toggle that bit, it initiates a move, and we see here that that move complete bit, or excuse me, that move clockwise bit is on, which sent that 0 over to our command bit, which means we're ready to go. Now, if I turn that bit off, when the motion stops, the moving bit goes off as well. So if you look here at our input registers, you see here now Our move complete bit is on, as well as move stopped or access stop bit. And our motor position has changed. We've actually got a motor position of 20,000 because we actually cycled through 2 relative move commands because that bit stayed on, cycled through a move. We had cleared the command word. As soon as it stopped, it sent the move again, and it was ready to go. It's that simple, and that's really all it takes to implement an AMCI Ethernet IP motion device in Studio 5000 using our EDS files. If you have any questions, feel free to reach out to AMCI either telephone or through our website at www.amci.com.